السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah, today we will, for some time, maybe 10 or 15 minutes, we'll continue the session that we were supposed to end last time, which is about deep networks, right? The remaining part is comparing between deep networks and channel networks, and trying to show you that deep networks have more attractive features than shallow networks. And in fact, the deep networks exhibited or showed much better performance than shallow networks in many applications in many areas, up to maybe 1,000 layers or more in some applications, in computer visions, in NLP, and reinforcement learning, in many applications and areas. And inshallah, in these few coming slides, we will discuss why is that. Okay, the first thing is to show you, or to compare between deep networks and shallow networks in terms of the ability to approximate any 1D function. We mentioned earlier that with the universal approximation theorem, we know that a shallow network can approximate any 1D function with enough hidden units, right? Now, do you agree with me that shallow networks in general is special case of deep networks, right? So just one layer, deep networks is more. And if we want to see or to reduce the deep network to be a shallow network, we can just arrange for the layers after the first one to just act as if it is the identity function. So it's like doing nothing. Okay, if that's the case, then we can say that the deep network can approximate any 1D function because it can be reduced to a shallow network. Okay, so in terms of this theorem, they are both the same. Anything that we can do with a shallow network, we can actually also do with a deep network. The second thing is the number of linear regions, and you will see a big difference here. We saw a similar plot to that when we talked about shallow networks, right? Here with deep networks, we are adding more layers. On the left side, we plot the number of parameters versus the number of regions. Okay, and the curves here, we are changing the number of layers. So where is the shallow network here in that plot? The first curve, right? When k is 1. Okay, so with k is 1, when we are changing the number of parameters, of course the number of regions is increasing. But with increasing the number of layers, we see that we have even more regions, right? And that's expected. So for this specific point, we have 5 layers. This is on the plot of 5 layers, right? The number of parameters is like 471 parameters. And in that case, we have 160,000 linear regions. So if we go to the y-axis, this is log scale again. This is more than 160,000 parameters, okay, with just 5 layers and 10 hidden units per layer. So this is huge. Now, if you look at this vertical line, this vertical line shows us that with the same number of parameters, how many regions we can get with different layers, with more layers. Okay, so we fix the number of parameters, and let's say that this is 470. Okay, with one layer, we can get about 100 regions. Okay, with 2 layers, we get more. With 3 layers, we get even more. With 4 layers, we can get more than 10,000 regions. Okay, this is with the same number of parameters. Okay, yani you can think of it like the same number, and roughly the same number of hidden units. Okay, instead of putting them all in one shallow, in one layer, okay, if we put them in multiple layers, then we can get even higher number of regions. Yes.
But how is it the same number of parameters if we add hidden units?
you can arrange, and if I give you the number of parameters, if I give you number of nodes of neurons, okay, you can arrange it in a network to get the same number of parameters. The architecture will be different, of course. Okay, and imagine. Okay, let me explain this even better. Let's say that we have a deep network with with three layers with a specific number of hidden units. Okay, we can calculate the number of parameters, right? Let's say that these are 1,000 parameters. If I told you with this 1,000 parameters, can you represent a shallow network or not? Yes, with with maybe more than 900 or close to 1,000 hidden units, right? So with the same number of parameters, these two networks will have different number of regions. Actually, with the deep network, we have even more. Yes.
On the second line, it says 10 units per layer. So
This is for the point here, for this point specifically. Yeah, for this point. Okay. So as we add more layers, the number of regions increases. If we fix even the number of parameters, okay, we'll have even more regions when we have more layers. On the right side, yes. Yes, when we add layers, we increase the depth. Yes. The what? Yes, of course. But this is what the curves are telling us. Okay, what these plots are, what these curves are telling us. Okay, with adding more layers, okay, the number of regions increase. Okay, even with the same number of parameters. Yeah. On the right side, we are okay. So on the left side, actually, we are plotting all of this when we have just one input. Okay, on the right side, it's the same plot, but when we have 10 inputs. And you can see the change in the scale here on the y-axis. Here, it's between 1 to million. Here, between 1 to 10 to the power 200. Okay, so the number of regions even increase a lot with more inputs. Specifically, this point, 5 layers again, 50 hidden units per layer. We have now 10,000 parameters or more, and with that we have more than 10 to the power 40 linear regions. Okay, so the number of regions really increases a lot with adding more layers and with adding more inputs or having more inputs. Okay, same idea here. If we look at same number of parameters, with increasing the number of layers, we have more regions. Although the number of parameters is the same. Okay, that means that if we have specific budget in terms of time or cost of computation, we can increase the complexity of the network by adding more layers, by arranging the same parameters within a network that is more deep than shallow one. Okay, is that clear? So this is telling it in summary. For a fixed parameter budget, deeper networks produce more linear regions than shallower ones. But we need to mention here is that these parameters, the number of parameters here in a deep network, are not all completely independent. There are some dependencies between the parameters. Okay, and that's because of the interaction between the layers. Weights are affected by the outputs of the previous layers and so on. So they are not all completely dependent. Whether this is similar to what we can see in real life or not, this is unknown. Some applications we can manage to use such deep networks to approximate the needed functions, and some are not. Yes. Not exactly that, but even with the feed forward, there are interactions between each layer, right? Each layer is interacting with the previous one. So the weights that are learned in between are affected by the previous layer. Okay, the output of the previous layer, which is affected by the weights and so on. So there is some dependency, of course. Yes, exactly. Even without these loops. Okay. Okay, so the third one is the third property we'll talk about here is very related to the previous one, which is called depth efficiency. Depth efficiency means that to approximate a specific function, we might need so many nodes in a shallow network. Okay? To approximate the same function with deep network, we might need much less number of nodes, much less number of parameters. Okay? That means that the deep network with less number of hidden units can approximate the same function that the shallow network can approximate with much more units. Okay, this is what we call depth efficiency. Again, in reality, we are not very sure that all of the real world functions work like that. Okay, but many of them, depending on, as showed in research and in several applications. But still, although this is attractive property, but it is unknown whether we really need that in real world functions or not. This one is really important, and we will talk about it, inshallah, later in the course. Large structured networks, deep networks can be viewed as large structured networks. Think about images. If we want to process images, first of all, the size of the image is huge, right? Millions of pixels. If we use fully connected network, then we need billions of links to process such images. Do we really need that? First of all, this is not practical to have such very large networks, but also, do we need that? Think of an image of that class. Okay, do I need to process every position? To recognize something like the chair or a table in that classroom, in the image of that classroom. Do I need to do that independently, or the same way of recognizing a chair will be the same regardless of the position of the chair in the image, right? It is the same, right? So we don't really need so many weights to do that, so many links to do that. We might share weights, and we'll get back, inshallah, to that later in the course when we talk about convolutional networks. You will see that to process parts of the image, we can do that with the same weights. Okay, we don't need to have different weights over the entire image to do specific task, like recognizing specific object in the image. Also, when we process images, we might need to do some processing on different levels of details. For example, first you might need to detect edges in the image. Then you recognize from the edges, you recognize shapes, and then you recognize objects like a chair or a table or a human face. And then putting all of these together, you might recognize a scene, right? So this is incremental, right? So you really need something that is structured that way to do the processing. You cannot do the processing all at once, like in shallow network. In deep network, allow us to do some interaction, to do some processing in sequence. Okay, and this is really can be done much easier, or actually can be done easily with deep networks, because we can add layers that can interact with the previous ones. And we cannot do that with a shallow network. Okay, so we cannot integrate actual information across the different levels of details of the image without adding more layers. Okay, so the idea from that is that the deep network allows us to do structured processing. Okay, processing that is done in sequence, because there is interaction between the hidden units or the neurons or the nodes across layers, and that's not done in shallow networks. The last attractive property of deep networks that we will discuss today is the fact that fitting deep models up to some specific depth is much easier than training shallow networks. And this is an example an experiment. This plot shows, forget about this word epoch now. Imagine that this x-axis is the size of the training data. Okay, so as we increase the size of the training data, we expect the performance to be better, right? We expect the error to be less over time as we add more training examples, right? And this is done in all of these curves. All of these curves are different with changing the number of hidden layers. So this one is with one hidden layer, which means a shallow network. And the others, this one is two hidden layers, this one is three, and this one is four. Okay. And you can see that, yes, the error is increasing with adding more training examples. But that's not the point of this plot. The point of this plot is that as we add more layers, the training is faster. Okay, the training is easier. Easier here means faster. Like how can we get that from the plot? You see all of the networks here, the experimental networks, reached almost zero error, right, at the end, right? But the one that has two hidden layers reached that much faster than, or with much less training data than the shallow one. And the one that has three hidden layers was even faster. Okay, the one that has four layers was faster. Okay, so we were able to fit the model to a good training error, or to a good performance much faster with less number of iterations over the training data, or with less number of training examples. Okay, and that's a feature of deep networks. To some extent, and beyond number of layers, it will get harder again. Okay, it will take a lot of time to do that, and we'll see some tricks. We'll discuss some tricks later to handle that. It is also the case that practically the generalization of deep networks is better. What do you mean by generalization? The performance on unseen data. Okay, so in general, the performance on unseen data with deep networks is better than shallow networks. Okay, any question on this? So we discussed now 4 or 5 properties that are attractive more with deep networks, and advantages with deep networks over shallow ones. Yes. Okay, when we say faster here, we are not talking about the time of the processing. Actually, overall time is also faster, but we mean here that we will reach the same performance faster with this number of training examples. Yani instead of taking, let me give you a concrete example. Instead of taking, for example, 2 hours, okay, to fit the model to a specific error, like 5% error, 2 hours with shallow network, maybe in 10 minutes we can get it with deep network. Getting the same error in less time, or you can think of it also in another way, getting better performance with the same time budget. Yani if you look at, if you plot a vertical line here, okay, this vertical line means that these are points that with the same time or the same training examples, right? Same number of training examples. The performance of the deep network is much better, okay? So with the same time budget, we can get better performance. And or with the same, to get the same performance, we can get it faster. You can look at it both ways. Okay? Any other questions? Okay, then I will ask. With same number of parameters, a deeper network generally has less or equal or more regions compared to shallow ones. That one is easy, right? More. Okay. Second one, depth efficiency means adding more hidden layers in a deep network can achieve equivalent approximation of shallow ones. A shallow network might need exponentially more hidden units to achieve equivalent approximation of a deep network. Raise your hand, please. Yes, Jermaine. So the second one? Okay, so the second one is the meaning actually of depth efficiency. Right? You agree with that? Do you agree with that? Okay, why not? So what is depth efficiency? What do we mean by depth efficiency? Huh? Yeah, as we add more layers, okay. When we add more layers, we we do that with much less cost than a shallow network that is doing the same job. Okay, right? Type. Which one of these then? First one or the second one? Or both? Type. Can we see from both sides? Yani it's either for the deep network we add more layers, okay, to approximate the same function that is approximated with the shallow network with much more nodes, right? Or we can do it from the other perspective, from the perspective of the shallow network. We can add more hidden units in the shallow network to approximate the same function that can be approximated with less nodes in a deep network. So both of them are correct. Actually, we are looking in each from different angle. Okay, from the angle of the shallow network or from the angle of the deep network, but both are the same. Okay, is that clear now? Is it clear now? Okay. Now we are done with this session. Where are we going from here? We studied linear regression, then we studied shallow networks, then we studied deep networks. Okay, but we don't know how to do the training. We know how these networks behave, I hope. Okay, but we don't know how we actually reach a model that is really good. And that's what we will, inshallah, discuss next. So we will discuss loss functions. We'll discuss how to do the to learn the weights and to compute the gradients. And then, inshallah, after that, we will discuss how to measure the performance of the model. Okay, any questions before we start the new session? Yes.
Okay, so like the question I got answered, but like in which situation would a shallow be like a shallow neural network be better than the
Okay, and this is good. This is the question for all of us actually. Which situation you think a shallow network can be better than a deep network? Simple problems, which means it's a simpler functions. Okay, in simple functions you don't really need deep network. Okay, maybe with the shallow one you might fit the model well. Okay, some tasks, not every task in reality is very complex, right? Some tasks are much simpler than the others. Okay, so in practice I wouldn't go for a deep network before I try a shallow network. But of course not with exponential number of hidden units, right? Otherwise this will be very costly, and it's much more efficient to do a deep network in this case. Now we'll switch to loss functions. Before that, let's recall some of the concepts that you went through in high school, I think, and also in the class in the first or second week. First, the logarithm and exponential functions. Okay, do you remember these functions? Okay, both are monotonically increasing. Okay, as we increase the input, the output will increase. When we talk about the logarithm function in this course, we will assume that the base is the Euler number e. Okay, so it is actually the natural logarithm, which sometimes we call it len. Okay, but we just use log in this course. But you know that the base is e. Quickly, some quick numbers about the logarithm function. What is log 1? Log 1 is 0, okay? And this is this point, actually. So this is 1, and the value is 0 here. How about log 0? Negative infinity. Okay, so it's negative infinity. Yeah, it's negative infinity. Okay, and it is increasing with increasing the input. And it is valid only for positive or non-negative numbers. Okay, for the exponential function, it takes any input, whether negative or positive, and it provides a positive value, actually. Okay, or at least non-negative value. What is e to the power 0? 1, okay, which is this point. What is e to the power minus infinity? 0, okay, 0. And of course, as we increase the input, the output is increasing. Okay, two quick rules about these two functions. Log of e to the power z is z, right? You studied that, I think, in high school. And log ab equals log a plus log b. We will use both rules, inshallah, in this session. Okay, so this is back from math. Now, earlier in the course, we discussed the loss function, right? What is the purpose of a loss function? What? Yes, so to measure how good or bad a model is, why is that? When do we need that? In training, when we do training, okay? In training, we need a guidance, okay? Whether the model that we reached in that moment in training, good or bad. Okay, so we need a single number, scalar number, that tells us is that good or bad. Okay, if we go through this direction, we will increase the loss function or decrease the loss function, and so on. Okay, so the loss function, of course, is defined given a training data. Okay, so we in neural networks, of course, we have pairs xi and yi. Okay, so the loss function actually is defined is a function out of the parameters of the model itself, and the training examples. Okay, and usually we just use the notation that it is a function of the parameters, but in reality it is function also of the training examples. Okay, why is it function of the training examples? Because we need to measure it on something that for which we have the ground truth, we have the predicted outputs, right? So that we can measure how good or bad the model is. And in training, we aim to find the values of the parameters that minimize that loss, because the loss is like a cost, like an error. Okay, so we want to find the values of the parameters of the model that will make the minimum possible loss, right? And remember this linear regression example. Okay, we had this training data, and we wanted to fit a line, so we used what we called at the time least squares loss function. Okay, and the least squares loss function was just measuring the square of the differences between the predictions and the actual ground truth values, okay, observed values. Okay, so these are the differences, and we just square them and sum them, and that's the loss function that we used here. That was just one example. Now, in this session, we want to know why exactly we used least squares for that type of problems. Is it just given from another planet that you should use this squares loss function, or what? And how, in general, we construct or we develop or we design loss functions for other types of problems. So if you are given a type of problem, you want to know which or how you can design your loss function. What loss function will be good for that type of models of problems? Sorry? Oh, okay, good question. The loss function is fixed for all problems? Of course not. Okay, of course not. Okay, for regression is different than binary classification, is different than multi-class classification. Okay, the type of problems in life is different, right? So you need to deal with every or different types of problems. Okay, and with different type of problems, the loss function will change. Okay, so we'll start with a concept that is very important called maximum likelihood concept. Okay, so far, first of all, in this session, the main objective is to find a general procedure, a general process of finding a good loss function for a given problem. So we are given a problem. How can I design in general? What are the steps that I should do to design a loss function that is good for that type of problems? Okay. So far, any model that we discussed, the linear regression or shallow networks or deep networks, we assume that the model predicts the output directly. Yani, for example, remember the classical simple problem of given the age of a child, predict the height? Whatever model that we design based on what we studied so far will directly provide the predicted height as the output, right? So we'll say the output is the height. And then we design either a shallow network or deep network with different layers and so on. But the output will be the predicted height of the child, right? So always so far, the model predicts the output given the input. Now we will switch that. Okay, we will change that to what? Instead of predicting the output, which means the model will produce one value, right? Instead of that, the model will produce a probability distribution over the possible outputs. Okay? It's a conditional probability distribution because it is conditioned on the input. So for any input, for any given input, the model, instead of producing just one number, it will produce a probability for each possible output. And if I have 10 possible outputs, it will produce a probability distribution over them, which means it will give us a probability for every single possible output of them, instead of just giving us one output. Kind of that. We'll talk about that. Okay, we'll talk about that. Okay, I will explain it more. Okay, wait, but just give it and get it in mind. Instead of predicting one number, it will predict a distribution of possible values. Type. Then, if we do that, then the loss function aims to make the predictions matching the probability of the observed output to be as high as possible. What does that mean? We said that the model will produce a probability distribution, right? So it will say for this value of the output, the probability is 10%. For this one is 20%. For this one is 50%, and so on, right? One of these only is the correct one, right? Based on the training data, right? And what is better is to give high probability for the correct value or low probability for the correct value? High probability for the correct value. And that's what the loss function will push the training to do. Okay, so the loss function will try to encourage giving high probability for the correct observed value for the given input. And for a given input, we know that what is the observed value, right? For a given input xi, we know yi. But the model doesn't know yi, right? The model will provide a probability for yi. If that probability is very high, then the loss should be high or low? Low, right? Because this is really good. If the probability of that observed value is low, then the loss should be very high. Okay, right. That still might not be very clear, right? So let me explain that in the next, I think, maybe 10 or 15 slides. Okay, first example, the regression example that I just mentioned, right? The age, given the age, what is the height? Okay, and these are the training data. Okay, now imagine that instead of providing, producing or predicting just one value for the height given the age, the model will produce a probability distribution. So, for example, this age, let's say that this age is what is 2.5 maybe years, right? So, what is the observed value for this input? The height, yeah, for it. What is the height for it? This point, right? So let's say that this is 1.1, okay, 1.1 meter, okay, for example. Okay, this is the observed value, right? Now, the model, previously, the model can produce one output, right? It can say, مثلا, 1 or 0.8, right? Now we'll change that. The model will not produce one number, it will produce a probability distribution like this one. What does that mean? The x-axis of that distribution, this is of course reversed, right? The x-axis of this distribution is all possible values of the output, which is what here? From 0, the height cannot be negative, right? Okay, so from 0 to whatever the maximum possible, let's say 2 meters. I don't think a child can be more than 2 meters high. Okay, so from 0 to 2 meters, and the y-axis, of course, is the probability. So this is actually a probability density function, if you remember from your probability class. Okay, and there is a probability for every possible value of the output. Okay, now what is the value of the output with the maximum probability here in this distribution? Probably this point, right? Yeah, it's very good actually. I think it's the same, but it's 1.1. So this actually probability distribution is really good because it assigned the highest probability to the actual output, okay, the correct output, which is 1.1. But still, it's not perfect, right? Because the probability of this point is not 1. It's maybe, I don't know, maybe 0.7. A better model should provide higher probability. So if it's 0.8, be even better. 0.9, as it's getting close to 1, it's even better, right? Okay, with me so far? So that can be the output of the model given this input. Another example, let's say that we have the input to be this point, okay? Now, the model will produce a different probability distribution. That's why we call it conditional. It's conditional on the input, okay? For a given input, the model will produce another or a different probability distribution. If you see here, these are different, right? Sorry. These are different, right? Okay. This one now is centered at maybe this is 2.5, 1.5. Okay. The other one was centered at 1.1. So you see the difference now between before we assumed that the output would be just one number. Now the output is a probability distribution. You can think of it, by the way, this way. The model now is not very certain of the output. So it captures its uncertainty within this probability distribution. So the model thinks that the output is 1.5, but with a probability of 60%. And it is less than 1 with probability 0 probably. Okay, and so on. Okay, so it indicates how uncertain or certain it is about the output with this probability distribution. Okay, type. You see, this is a probability distribution that I think is very familiar to us, right? Do you remember the shape of this? The normal distribution, the Gaussian distribution, right? The normal distribution has two parameters, right? What are the two parameters? The mean and the variance. Okay, the mean is where the distribution is centered, and the variance is the width of the bell shape, right? Right. This variance, if it is smaller, okay, and the center is actually matching the um, with the correct answer, that means that the probability of the center will be higher, right? So actually, the distribution even can have different parameters, right? Yeah, the model can produce a distribution that is more certain about the outcome than another. And if this is flattened, okay, so if the variance is really high, then this is indicating that the model is not very certain, okay, than the one that has lower variance. Okay. Here's another example. Yeah, do you have a question? Any questions? You had a question, I think. You? No? Yes, okay, go ahead. Okay, good question. In training, we always use the pairs that we have in the training set. So we are sure that we have a pair with that input and that output. Okay, so there must be an output for that input. Okay, that we will compare the predicted output with. Okay, type in reality, after we build the model, can we use it for inputs that were not in the training? Of course, yes, because now the model is general for any input. But to train it, we have to compare with something that is observed. Okay, so we have to go through the points that we already observed in the training set. Okay, so here's another example. In that example, the input is a number of words in an email, and we want to predict whether the email is spam or not. It's very simplistic, right? With just the number of words in the email, we want to predict whether the email is spam or not. Okay, so we have how many possible outputs here? Only two. In the previous one, it was continuous. Okay, that's why it was a regression problem, right? Here, we have just two. Okay, possible outputs. Here, it's infinite, right? Yeah, and continuous values, right? So this is regression. In that example, we have only two possible outputs, spam or not. Okay, it is binary. Okay, so the distribution, the output distribution, okay, of the model now has to be continuous or discrete. Discrete. Okay, so for example, for this point, it has to give a probability for 0 or 1. 0 means not spam, 1 means spam. So it will be a discrete distribution. Can we use the normal distribution here? No, normal distribution is for continuous variables, right? This is a discrete variable, so we have to find the appropriate probability distribution for that type of input, for that type of output. Okay. So here, for example, the model produces this this distribution, okay, which means that it prefers not spam, but not very sure, right? It's maybe 60-40. Okay, a better distribution of for that will be maybe 80-20 or 90-10, right? Of course, based on the correct answer, which is not spam actually. Okay, here's another one. We have here we have it's a spam. The model still is good. It's not bad. Okay, and it's even better from the previous case because it gave the correct label higher probability. It's still not 100%, by the way. So the model will be penalized here, okay, but not as much as it will be penalized in this case, right? Because here the probability of the correct label is it's much closer to 1 than in this case. Okay, so you got the idea? So the loss function should capture this. The loss function should give us high penalty when the model is not very certain, or if the model is very uncertain about the correct label, and low penalty if the model is certain of the correct label. The model assigned a high probability for the correct label. Okay, yes.
In the regression problem.
Yeah, should we get back here? Yeah.
When we had the right, and we have like the probability, like the probability distribution, we have many values, right?
Yes.
Is it possible to take a lot of these values and then do classification on them?
Okay. Okay, so you are saying, is it possible to just live with the probability distribution as an output and then do something with it? It depends on the application. Depends on what do you want to do next with the output of that model. Okay, if you want to process this output with a next classifier, another classifier, yes, you can take the entire probability distribution. But if you want to show that to the user, of course, you will not show the user a probability distribution, right? You need to show one value. In this case, the best possible strategy is to show the value that has the highest probability. Exactly. Which should be maximized in the loss function, and you will see that. Okay, and that's why it's called maximum likelihood. Okay, we will maximize the probability of the observed value, of the observed output value. Now we are talking about loss function, right? The goal of the loss function is to show that there is an error. Okay, so if the error is high, that means that the model is not doing good, which means penalty here. That's what I mean by penalty. Okay, the penalty means the loss will be high. Okay, whenever the model is making mistakes, is making large mistakes, okay, big mistakes. Okay, any other questions? So we'll stop here inshallah and we'll continue next time. Assalamu alaikum wa rahmatullahi wa barakatuh.